Hello everyone, welcome back to Introduction to Semiconductor Devices. In the last lecture, we introduced the concept of doping. We explained qualitatively what happens when we introduce uh, dopants into the semiconductor, and then we talked about how the Fermi levels change in a semiconductor. So quick recap. So we said that there are two types of semiconductors, N-type semiconductors and P-type semiconductors. We get N-type semiconductors when we introduce uh, donor atoms into the lattice. For example, it could be arsenic, it could be phosphorus. So when we introduce these elements, these are group 5 elements. So these are group 5 elements. And so they have 5 electrons in the outermost shell. So that single additional electron is going to go into the lattice and then it will contribute to electrons. Okay. And so we have majority carriers as electrons in an N-type semiconductor, and the concentration of electrons would be essentially given with the doping density. If you have more dopant atoms, you have more electrons. And we also saw that there is a relation which is NP product equal to Ni square, N naught P naught equal to Ni square. And from that you could calculate the number of minority carriers which are holes, and that will turn out to be some number which is given by expression here. So analogously, we also looked at P-type semiconductors, wherein if you, let's say, put boron into the lattice, it is group 3 element, boron, and so it requires one more electron, and so that it can form 8 covalent bonds with it can share 8 electrons with the neighboring silicon atoms. So because of that, it will accept an electron from the silicon lattice and becomes negatively charged, okay? And it creates a hole in the process. We saw this. So in P-type semiconductors, the majority carriers are the holes and the minority carriers are the electrons. So these are exactly reverse of what it was in the N-type semiconductor. So we also saw how the Fermi level changes when you change the doping density. So we said that if you have very less number of dopants, then essentially the number of electrons or holes being introduced is very, very small compared to the intrinsic carrier density, and the Fermi level would be close to the EI. Okay? But as you increase, let's say, the donor density, the number of electrons increases, and slowly the conduction band moves towards the Fermi level moves towards the conduction band. And similarly, for acceptor density, if it increases, the Fermi level moves towards the valence band. And we also noted that this difference here, basically EC minus EF in the case of conduction band and EF minus EV in the case of valence band, is very, very important. We said that these numbers should be greater than 3 kT. The reason we said that was because if you have the Fermi level closer than this 3 kT, then the doping tends to be, it's basically, we say that it's a degenerate doping level. We don't like it. Okay, the expressions we give are actually only valid for non-degenerate doping. When you have non-degenerate doping, we are okay. Okay, otherwise we have to take additional expressions and it becomes a little bit more complicated. Okay, we won't deal with that. You might ask a question. Now we have all this, phosphorus, arsenic, boron. Why only those elements? Why not other elements? Okay, to understand that, we have to look back at the origin, okay, of how these bands are forming. We have the silicon lattice and you have the bands, conduction and valence bands. We have seen it multiple times. Now these dopant atoms are essentially like defects in the lattice. Okay, if you have a lot of dopant atoms, then they'll actually form defect bands. But generally the defects, or the dopants, are going to be smaller in number, so we can represent them by an energy level. And we saw this already in the last lecture. We said that the donor level is going to be slightly below the EC and the acceptor level is going to be slightly above EV. But how did we come to that? Well, you could actually calculate the energy levels. We can actually calculate how a defect in a silicon lattice behaves, and then we can determine what the energy level of the defect is. Okay, and here some of the examples are shown. For example, phosphorus. Ionized phosphorus has a ionization energy. Phosphorus has an ionization energy of about 45 milli electron volts. Similarly, arsenic has about 50 milli electron volts, and boron has about 45 milli electron volts. So what this tells us is that the energy is quite close to the conduction band. These are ionization energies in silicon lattice. Okay, so these three elements have energies which are very close to the conduction and valence bands, and that's why they can be used as acceptors and donors. Okay, so why not other elements? Let's take a few examples here. So there are many different examples, elements which are shown here, but to us the important things are zinc, manganese, copper, gold. So these have defect levels or the energy levels which are very, very in the center of the band. and these become very, very critical for us. Okay, and of course there are many other, like tin and zinc, indium, and so on, which also can contribute to energy levels in between that band. Okay. So the reason we are particularly interested in these mid gap levels, these four of these, right, which I have highlighted here, these are known as the mid gap levels. Okay, mid gap, defects, you can call it if you want. Okay, the reason we are interested in is we will, first of all, we try to make sure the semiconductor is extremely pure so that it doesn't have any of these defects. Okay? That's why we say that, it's 9N purity, we said, right? The reason we ensure that is even if you have a small trace amount of zinc or manganese or, then it causes defect levels and that can cause to problems in current conduction. Okay? That's why we purify it. And then deliberately introduce arsenic or boron or phosphorus, one of them. We try to make sure that there are no other defects present. But by chance, in the fabrication process, some amount of gold or zinc got in. What would happen? Okay, we are saying that the defect level is close to the mid gap, right, in the middle of the band gap. So what could happen is the zinc or a gold dopant can act like a trap center. Initially we said electrons are going to get excited from electron hole pairs are created when electrons jump from valence band to conduction band, right? That is one of the processes driving the equilibrium, and the opposite process was the recombination. So it so happens that if you have a trap center right in the middle, then it can actually trap an electron from the conduction band. So it will trap it. Similarly, it can also trap a hole from the valence band. Okay. And because the energy differences now are only Eg by 2, in the previous case for electron and hole to recombine, the energy difference was Eg and it was less probable. But if you have the energy differences of Eg by 2, this sort of a trapping behavior is much more probable and it will actually cause dissipate, it will recombine, electrons and holes will recombine and dissipate as heat. And we don't like that in semiconductor devices. That's why we don't like these, energy levels which are in the middle of the band. Okay. So we will stick to phosphorus, arsenic, and boron in our uh, rest of the lecture today. All right. So now let me ask you a question. We saw how the Fermi level changes with the doping density. How does it change with temperature? If you want to analyze that, we'll have to look at the expression, right? Because we are interested in plotting. For example, I'm interested in plotting. Let me say I have EC, EV. And now the question I'm asking is, as I change the temperature, what would happen to the Fermi level? Let's say initially the Fermi level was somewhere, let's take some doping density. I don't know. Maybe you could take 10 power 15 donors. If you take that, for example, this is EI, right? Let's start with ND of 10 power 15 per centimeter cube. If you do that, what happens is, let's say the Fermi level was originally somewhere in here. Okay, that's the initial point. Now, let's say this is at room temperature. Okay, this is at RT, room temperature. Now, as I increase temperature, what happens to the Fermi level? Okay, think about it. Take a moment. Okay. If you look at this expression here, right, which is given on the left, it says that EF minus EI is going to be KT ND by NI. So, as the temperature increases, does the EF minus EI increase? Okay, that's a question that you should ask. Okay, so will it go like this? This is EF minus EI, right? As temperature increases, does this happen? Okay, it's a question. Please think about it carefully. Okay. And by the way, how did we get this expression? EF minus EI equal to KT ln ND by NI. Remember, this last time we derived this expression, or we gave you this expression. We said that N is equal to Ni exponential. We said Ni, the reference level is intrinsic level, so that has minimum carrier density. And now, if you add dopants, it's going to increase, right? So your exponential is going to have EF minus EI by KT. So as you increase the doping density, EF goes closer to EC, and so EF minus EI increases, and therefore the electron concentration increases. And you can rewrite this in this form here. Similarly, you'll have an expression for holes. Okay. So now, what will happen to the doping density as you change the temperature? Or rather, what will happen to the Fermi level as you change the temperature? Well, what I have shown here, this is wrong. It won't happen like this. The reason is Ni also exhibits temperature. exhibits temperature dependence. You know, I really like this sort of graphs which will tell you, qualitatively what happens with changes in temperature, doping density, and so on. Because if you're able to correctly draw these graphs, you understand quite a lot of physics. So please try to make sure that you are independently able to explain the graphs. Whenever you see a graph, showing some parameters varying, please think about it. That will really help clear up a lot of concepts for you. Okay. So now, how does the temperature influence the doping density? We saw this in the last or the fourth lecture, I believe, wherein we said that if you have an extrinsic semiconductor, and this is your temperature, and this is your doping density, let's say electron density. So initially, you had the partial ionization regime, and then there is an extrinsic regime, and then there is an intrinsic regime. We said. So this is for a let's say ND doping. Okay, let's some number. Okay. And correspondingly, you also have another curve, which was the intrinsic part. So as you change, as you increase temperature, more and more electron hole pairs are generated. So this is your intrinsic, right? And this is your extrinsic semiconductor, you could say, right? So as you increase temperature, this is what is happening. So now, physically, think about what's happening. You should not see much of temperature variation, right? Whenever your semiconductor is in the extrinsic regime here, you should not see any changes in the Fermi level with temperature. But once that semiconductor reaches the intrinsic regime, then you start seeing that the number of electrons is going to be equivalent to the intrinsic carrier density, right? So the intrinsic carrier density is going to drive your electron hole pair, electron concentration. And we know that whenever it's in the intrinsic regime, EF has to be, EF is at EI. Because intrinsic semiconductor EF has to be EI. We proved it actually in one of the lectures, in the last lecture I believe. So what should happen now? So it looks like as you increase temperature, semiconductor becomes intrinsic. That means you have the electron hole pair generation, which is dominant, and which will take the Fermi level close to the EF. Okay. So please think about it for a moment. Try to draw take ND equal to 10 power 15, ND equal to 10 power 18, and let's say draw for these two per centimeter cube. Of course, everything is per centimeter cube whenever I talk of density. So please draw the graph for this and verify whether what you're getting, and then you can compare it with this expression, this graph here. So this is what happens. So as we said, as temperature increases, the semiconductor becomes more and more intrinsic. And of course, if your doping density is high, it takes higher temperature to make it intrinsic. But if your doping density is low, it quickly becomes intrinsic. Okay. So N-type, P-type. Okay. So please make sure that you understand these things. Even though, yeah, in a paper-based exam, I typically ask these questions because it gives a lot of insight into the understanding of the student.